right, you have that same population of quasars now lensed. Because these are quasars, you're not seeing any shear, but what's happened is the size of the quasar now has been scaled to indicate the amount of amplification of the flux for the quasars. So the quasars near the lensing source get brighter, and we all know this. But the other part that's less obvious is the fact that because things are getting deflected by the gravitational potential, the density of the quasars on the sky, for any given circle near the lens, you're going to find fewer quasars than you would over here. And so this dilution of the density is the second part of the magnification. So if we do this, do some math, because life is not all looking at pretty pictures, or at least most people's lives. Mine is, but
real life.
So if we have flux from a given source, that gets magnified by some factor mu, so it increases the flux that we observe above the natural flux of that object. If we then have a collection of objects that are all brighter than some flux limit, we're going to observe a number count relation that's equivalent to the brighter flux that you get due to the magnification, but because the deflection, the dilution factor figures in, that's actually going to reduce the number density by a 1 over mu factor. And so if we convert this into magnitude space, because eventually we have to look at this with objects from catalogs and that sort of thing, you end up with the relation there at the bottom. And just to sort of put this into graphical form, what you find is that the amplification and the dilution have fixed strengths, right? Which makes sense because they're both the same factor mu. And so if you have a relatively shallow sample, you're going to get diluted by the deflection of samples, and then you're going to get amplified, which is going to push you this way because this is magnitude, so you're going to get pushed to smaller magnitudes. And so you see that if the slope of this thing starts off shallow, the red line that you end up at ends up being a relative suppression of the density compared to what you started out with, the sort of true sample in the green. Whereas the same deflections, if the slope is steep, will end up giving you an enhancement of the density because the amplification wins out over the dilution. Now, if we were able to measure, if we knew what this green line was ab initio, we would be done here. All we had to do is just measure the number counts and compare it to what the reality or what the true number count signal was, and we'd be finished. We don't know what the green line is, so we have to do something else. And so what we do is we cross-correlate the background sample, which in our case are quasars, against a foreground sample. Now, there are a lot of words here. You don't have to read them all. There are just three things to take away from this. First of all, the signal in principle, the cross-correlation starts off as something that's a function of angular separation between the lens and the source, or lens and the quasar, and the magnitude of the quasar, right? Because the alpha value, the value of the slope can change as a function of magnitude. However, for quasars, magnitude and redshift end up being basically decoupled, right? The magnitude of quasar doesn't really tell you anything about its redshift, and so we can actually separate things out in the second line. So all of the lensing kernel, the geometry, all that sort of thing, we pull that out into something that is going to basically be constant as a function of magnitude. Because if we separate our quasars into magnitude bins, as we'll do later on, the lensing kernel is not going to change because the redshift distribution of the quasars basically stays the same, and the lensing kernel is broad enough that it doesn't really change. So we factor all of that stuff into this W naught of theta, and that gives us this free parameter, alpha minus 1, as a function of magnitude. So as we vary the magnitude, it's really that prefactor that's going to change. And so if we start with if we have a sample where alpha is greater than 1, we expect from the previous slide that the density is going to be, the amplification of the density is going to win over the dilution effects from the lensing, and so we're going to see a positive cross-correlation between our galaxies and our quasars. And if it's less than 1, then we'll see an anti-correlation. Now, the universe being largely indifferent to things like people making tenure, the value of alpha that you find for field galaxies, the most abundant source of lenses that you could, or of lensed objects that you could possibly get, ends up being about 1. So for most galaxies, if you took like a background sample of field galaxies and a foreground sample of galaxies as your lenses, you would observe exactly nothing, which is hard to write a paper about. So in order to get a signal out, what you end up having to do is you end up having to go to subsamples. So you can do luminous red galaxies, which tend to have fairly flat slopes. In our case, we do quasars. So as I said at the top, the quasars are really, from a data side, the quasars are sort of the star of the show. So people have tried to do this in the past. They've done it with radio samples of quasars, with optical samples of quasars, and the results can be charitably described as mixed. So we did what is the common practice of Sloan. We hit the data with, or hit the problem with the biggest data set that we could possibly get our hands on. So in an optical survey like Sloan, you sort of typically do quasar target selection the way that Sloan's spectroscopic sample does it, which is you look at plots of quasars and stars in these color diagrams. You draw a line between the stars over there and the quasars over there, and you say, okay, we're going to target this stuff. And if you're the people who work on the quasar target selection, this turns into a selection script that's, Robert, how many lines? Close to it. Yeah, it's close. It's like a 1,000-line shell script. It's scary.
Not shell, tickle.
Tickle, yeah, even worse. So, but amazingly enough, because the Sloan photometry is good and kind and wise, that actually works surprisingly well. So, for quasars brighter than 19th magnitude, 85% of the time that you put a fiber on an object and say, I really believe that this is a quasar, it turns out it is. And compared to previous surveys where you were lucky to get 50%, 85% is a great number. But the reality is that quasars don't live in projections of 2D color space, at least in Sloan. They actually live in a 4-dimensional color space. And so you'd like to take advantage of that fact. And thanks to some work with some actual computer science and statisticians at Carnegie Mellon, Gordon was able to put together this kernel density estimator method, which uses the full 4-dimensional information. And what you're seeing here is, so the black contours are basically the quasars that you would get based on Gordon's 2-dimensional color cuts. The red contours are the extra bit you get from the KDE method. And while visually this doesn't look as impressive as it might, because it's a weird contour plot and everything's kind of overlapping, the facts on the ground are that when you apply this method to the quasar data set, you're able to increase the efficiency of your quasar identification to better than 95%, and you're able to go 2 magnitudes fainter. And since this is a game that in the past had been dominated by Poisson statistics, a factor of 10 in your number density is a gigantic win. The other thing that sort of plagued this game in the past is the thing that shows up in any sort of magnification measurement, which is you have to make sure that your two samples, your lenses and your sources, are well separated in redshift. If the intrinsic cross correlation between these two samples is much larger than any lensing signal, and so you really got to make sure that these things are well separated. And so, since this is a purely photometric sample, we have to use photometric redshifts, which, absent any other information, you would think with quasars would be an absolute disaster, because the primary feature of a quasar spectrum is that it's a power law. And the problem with that is if you redshift a power law, it's still a power law. So that's no good. But because quasars also have the strong emission lines, you can actually see the effect of the emission lines moving through the filters, and that's what this plot shows here. Now, it's not like galaxy spectra where things move sort of uniformly and nicely to the red. Because these things move in, these strong emission lines move in and out of the filters, and some emission lines are stronger than others, the colors end up jumping around. And so the errors that you get out of this are so not Gaussian, we can't even pretend that they're Gaussian like we do with photometric redshifts for galaxies. And so you can't start with that fiction. You actually have to say, okay, I have a lower limit and an upper limit on the redshift of this quasar, and I'm going to give you the integrated probability of this distribution that the redshift really is within this range. And that's what we use. And so for the average value of that integrated likelihood for our sample is about 85%. So we're reasonably certain that we're getting the quasars that we think we are. So just to sort of set the stage for the measurement results, so this is the redshift distribution that you get for a sample of R between 17 and 21 Sloan galaxies, peaking around a redshift of 0.3. This is the sample, or this is the redshift distribution you get for the quasars after we've applied our photometric redshift cut between 1 and 2.2. Over here, you see the number counts of the quasars, which are, so we say, pretentiously color-coded to indicate the samples that we're going to eventually break them up into. So we start with the Brice sample, where the average value of this alpha minus 1 parameter is 0.95. As we go to fainter and fainter samples, you can see that the alpha minus 1 decreases, is about 0, and then turns over and ends up negative. And this is now alpha as a function of, alpha minus 1 as a function of magnitude. So long story short, when we split up our sample, we expect to see a positive cross correlation between bright quasars in our galaxy sample, a null signal in the middle, and then an anti-correlation at the faint end. And this is what we actually get. So you can see up here the magnitude limits used for the different samples. The data points are the actual measurements. The red dashed line is what we get based on the alpha minus 1, based on a fixed angular model for what the correlation should look like, and just putting in the alpha minus 1 values that we get for measuring the number counts. And then the black lines with the errors are the results of actually fitting for the alpha minus 1 value that best matches the measurement. And you can see it pretty much works, right? The bright quasars, when you cross-correlate them, give us a positive signal. In the middle, we get an or we get no signal at all, basically. And then on the faint end, we end up with an anti-correlation. And the red dashed lines are within the error contours, and all is golden. So that's a paper, right? But when you see this, you say, okay, well, this is great, but can we do any better? And in fact, we can. So the problem with this is you can't take the whole sample in one piece, because even though these are quasars, which I told you are a subsample, which are good for lensing, if you integrate alpha minus 1 for the full sample, alpha minus 1 ends up being very close to 0. So you can't just do this for everything and call it a day. What you actually have to do is do this optimal estimator that Brice developed, which is to basically weight each quasar by the alpha minus 1 value appropriate to its magnitude. And so what you're doing here is you're effectively taking the anti-correlation that you see at the faint end and multiplying that by a negative number, so you flip it over. And so now instead of canceling out the positive correlation at the bright end, it actually adds coherently. And so you end up with this measurement here. So this is, as it says here, this is an 8 sigma detection. The theory curve and the data and the actual measurement curve are spot on. That it's much easier to talk about things that don't quite work as opposed to things that actually did work, and this actually worked.
Why not just measure W0 theta given your model here in the data?
Why not measure it ab initio?
No.
Or
I don't know why. Is this an optimal weighting? Is it the same thing you'd get if you just took this model plus with alpha b minus 1 times W0 theta plus errors and did an optimal, and you know alpha minus 1 for each sample?
Right. Well, that's but this is equivalent to having 100,000 separate samples, right? We're doing this on a quasar by quasar basis. So it's even better than taking our previous samples and adding them up correctly. This is actually done on an object by object basis. So this is really an optimal the optimal way to do it, right? Yeah.
So you're using alpha of n where n is the observed magnitude?
Yes.
That's different from intrinsic magnitude. Is that biasing the results in any way?
There is a slight degree of bias because it is a lensed magnitude, right? But mu is very close to 1, so it's a small. So relative to the error on the magnitude itself, it should be a small effect.
What are the theory terms?
So it's just a generic halo model angular correlation. You wrote that. We wrote the paper together. You know what the theory curves are. Not only are you on this paper, you're on the other theory paper where we actually did the theory curves for this thing. You know what the model is.
Okay, why are there two theory curves?
No. The red dashed line is the theory curve multiplied by the value of alpha minus 1 that we expect just from looking at the number count. So it's sort of the real theory curve. The black line is the best fit to the theory curve. I'm sorry?
Is the best fit to the data?
Best fit of the data to with the angular correlation model that we have. Yeah.
Is this DR6?
No. That's the thing. This is DR3. This is like back. Well, this is 2005, right? So, and even for 2005, it was a little bit small. But this is the quasars that we had at the time. Is what drove this basically. So as dead sexy as that is, the thing that's even better is this. So this is the covariance matrix of this measurement. Now, when we did this, you'll notice the binning here. So if you have a good eye for logarithmic binning, the binning here is kind of funky. It's not actually a true logarithmic binning. It's this hybrid logarithmic binning that I developed because we expected, and in fact, I mean, when you look at the measurements where we split things up, at the small angle limit, you were getting dominated by Poisson errors. But when we add everything up, this is not the covariance matrix that you get from a measurement that is dominated by Poisson error, right? If it was dominated by Poisson error, what you'd expect is you expect the errors to be blowing up as you go to smaller and smaller scales. That's not happening. This is a covariance matrix that's consistent with the idea that we're dominated now not by Poisson error, but by by cosmic variance error. So even though this is an 8 sigma result, we actually choked at the last minute because we could have made this an even stronger result because we can push to smaller angles, as Brice will show in the middle in a minute. This is an 8 sigma result, but it's actually more than that. We haven't actually done the calculation of what it is, but the point is, with the quasar sample that we've got now, we've moved out of the regime where we're just sort of fighting to detect this thing and work with it, but we're actually in the regime where this is something that's cosmic variance limited. It's something we can actually use to do real science. And so the last thing I'm going to show before turning this over to Brice is the other thing that we didn't have in our paper, which is the actual conversion of this into something that is physically meaningful, which is always handy. So this is now the mean magnification excess as a function of angle for our sample. So this is something you could actually directly compare to the results you get out of like the galaxy weak lensing done with the Sloan spectroscopic sample. So this is setting the stage. Now Brice is going to take it home.
So the question, how did you get the covariance matrix on the previous law?
So that was done with jackknife error bars or jackknife samples.
On the data, on the one data set only.
Yes. Yeah. So it's jackknife voodoo that I don't claim to be. I don't claim that it's exactly what you'd want to do, but it's sort of serviceable.
What was the galaxy sample?
The galaxy sample are just Sloan photometric galaxies between R of 17 and 21.
Is magnification excess different from magnification?
Yeah, magnification excess is the excess with respect to unity. So this is, the magnification is 1 plus this.
So this is mu.
Now this is mu minus 1. And this is in percent. Huh?
This is percent.
So yeah, so at 1 arc minute you have a mu of about, an excess magnification of about 1%. Okay. So let's move on. So far, Ryan has been talking about, so this is the estimator that we use in our first paper. So it's basically measuring magnification through correlations between number counts or density changes. This is written here. So what Ryan showed is a correlation between number counts of quasars, which is an estimator of the magnification, and the number counts of galaxies or the densities. So this is the key quantity that was used. So recently we started to use a different approach, which consists in looking at the correlation between the magnitude change of quasars and the densities of galaxies. So as Ryan showed at the beginning, magnification amplifies the flux of these background sources. So we know that the sources have to be brighter. So that's also something we can measure. So those two things are related, but they are not exactly the same, and they have different characteristics. So if we have magnification only, then the magnitude change of a quasar is simply going to be related to this quantity, where mu is the magnification. And so that's something we can directly measure with the data. All right, so the way it works, just for you to notice, if this is the number of objects as a function of magnitude, with a limiting magnitude here, if we start with the green line, we turn on magnification effects, we will have a shift. Now if we ask the question, what is the change in the mean magnitude of the sample, the answer is 0. Okay, the mean magnitude is going to be a given value. If we turn on lensing, we will find exactly the same value because the shape of this curve is exactly the same. And this is due to the fact that some new objects enter the sample, and they compensate the fact that some objects get brighter. So there is also an increase of the number of faint objects, and for this kind of simple relation, which is a power law luminosity function, there is an exact cancellation between the two. So we cannot observe any change in the mean magnitude of the sample, if it is lensed or not. The only hope we can have to see something is if there is a departure from a power law. In that case, there is a change in the mean magnitude, and that's what we can try to measure in the data set. As Ryan showed, the number counts for quasars, they show a continuous change of slope, the number of quasars as a function of magnitude. So with quasars, we are lucky we are in this regime, so we can hope to see something. So if we use the same sample of the same data set, this is what we get when we try to measure this estimator. So here what I'm plotting is the correlation between the magnitude change of quasars and the galaxy over density. So the first thing to notice, this is negative. So we are seeing an anti-correlation between those two quantities. In other words, when the overdensity of galaxies increases, the magnitude change decreases, which means that the objects are becoming brighter. So what we are seeing here is the brightening of quasars as they get closer and closer to galaxies angularly in the sky. So this is the same effect, but now it's measured with a different estimator. With this analysis, we have been able to push the measurement both towards smaller scales and larger scales. So now we are spanning more than 3 orders of magnitude in scales. This is the physical scale at redshift 0.3. So that's quite impressive. And you can notice something else here. This is what we find if we measure this quantity in 2 different bands, I and J, so red and blue. As you can see, the results in blue are systematically closer to 0 compared to the results in the red. So there is an effect that is happening on top of the magnification. And this is very well consistent with the fact of having some dust extinction as well as magnification. So if there is some dust on large scales around galaxies, so when light rays are going to go through galactic halos, there will be some magnification and some dust extinction, which is wavelength dependent. So this looks like what we are seeing here. Now if we look at the measurement on small scales, this is now shown in the 5 SDSS filters. We see that there is a continuous effect if we go from blue to red. And this is again consistent with dust extinction. So dust extinction is usually stronger in the blue, so it competes with magnification and makes this magnitude shift smaller in blue bands. So yeah, we think we are seeing both magnification and dust extinction. And we can actually now go after a third quantity. So Ryan talked about this density estimator. This is the magnitude change estimator. We can also look at the correlation between galaxy over density and quasar color change. So if the magnitude shift is due to these two terms, and if we look at the color change, then magnification cancels out, and we are going to probe only the term due to dust extinction. So that's something we can do, and this is what we get. So I'm showing here the 10 color combinations that we can measure with the SDSS, and this is now the correlation between quasar colors into different filters, galaxy over density. This time it is a positive correlation, so there's a positive correlation between quasar reddening and galaxy over density. It's detected in all color combinations. And again, we can measure this effect on an impressive range of scales, from scales as small as like 25 kiloparsecs around galaxies all the way to 20 megaparsec or so. So that's quite nice, and this is new. This is the first detection of dust reddening on large scales around galaxies. When I say large, it's larger than 50 kpc, let's say. I'm not aware of any other results in the literature. What else can I say? Let me continue. The only attempt of such a measurement that I have found so far is a paper by Zaritsky in '94. He looked at foreground and background galaxies and looked at the color change, and he called that a preliminary evidence for dust. He got a data point here, which is at around 50 kpc, but nothing on larger scales. And very surprisingly, as far as I know, nobody has tried to redo that between '94 and now. So that's why we are going basically from this plot to that plot, which is a huge difference. And this is going to be very interesting for people who are interested in dust, the distribution of dust on large scales around galaxies. And again, so we are probing galactic halo scales, and we are going all the way to large scale structures in this plot. So this is really probing basically cosmic dust or intergalactic dust. So dust has some well-known wavelengths dependence. This is just an example of the cloud of dust in our galaxy. But the important thing here is that we know how dust extinction curves look like as a function of wavelengths. Okay, this is showing yes, these dependencies for the Milky Way, the SMC, and the LMC. And in our measurement, we have some information as a function of wavelengths. We have here 4 independent colors. So we can also ask ourselves whether our wavelength dependence makes sense for this. I mean, how does it compare to classical dust extinction curves? So by doing so, we can just take these 4 independent colors, or a combination of 4 independent colors, and this is the extinction curve that we get. So here I'm showing results on small scales and large scales. So the angular scale is here. This corresponds to scales that are smaller than 100 kpc around galaxies, and this is larger scales. And I'm showing 4 colors, so everything is done with respect to the R band. And this is the reddening that we find, basically, with the data points. The blue curve is a fit if I use the standard O'Donnell extinction curve, out of which I can extract AV and RV, the quantities that people like to see when they talk about dust. And just as a reference, the dashed green curve here is the standard galactic dust extinction curve with RV of 3. So what we find is something which seems to be in a good agreement with classic standard type of dust. So actually on large scales, our fit is giving a value which is really close to the standard RV of 3.1, so the two curves are on top of each other. So this shows that the signal that we are seeing as a function of wavelengths has the expected dependence of dust extinction. Yes, Ken?
What redshift did you put your dust at to do this?
Redshift 0.3. But it's very similar to redshift 0 because it doesn't matter much. But this is done at redshift 0.3, which is a median redshift of our galaxy. So
we should say that the galaxies here are a somewhat different sample than the previous set of galaxies. These are now 17 to 21 and a half in I. So it's a deeper sample that we need to drive the number density up.
Yeah, so we are going a bit deeper with the galaxy population here. Okay, so that's quite interesting, especially for people who want to study dust. And we can just extract some interesting quantities out of that very quickly. So now, if I just assume an RV value of 3, just to as a reference and to reduce the error bars, I can infer the profile of extinction in the V-band, which is shown here. So this is the mean extinction profile around galaxies that we get out of this measurement. That's a quantity which is going to be useful for two reasons. First, it tells us what is the mean extinction we can have along lines of sight in the universe. And again, this is a regime that was not proved before. And for people who are interested in dust, it tells us how much dust we have on large scales around galaxies and galactic halos. And then it may allow to answer questions like, where is this dust coming from? Are we seeing dust in satellites, or are we seeing dust which is in outflows and ejected on large scales around galaxies? So those are questions we should be able to answer.
So how does this compare to like estimates of magnesium-2 column depths versus impact?
So with magnesium-2, it's hard to get a column density because usually the lines are saturated. But the reddening we find in magnesium-2 systems is in a good agreement with the reddening we find with this technique on scales of about like 50 kpc, where we have data for both. So it seems to match up. Okay, so now if we go back to our first measurement, so here, what I showed initially, so the main effect that we are seeing is magnification. Quasars are getting brighter and brighter. But if we want to really extract the magnification here, we need to correct for dust extinction. Okay, and we have seen previously that we are seeing a standard type of dust with a value of RV of 3, and this RV of 3 corresponds in a different description of a power index of -1.2 for the extinction curve. So we know that the signal we are seeing can be described by this. And now what we can do, we can just fit these data points with this formula. We can just take the limit when lambda is infinity, and then we have the magnification only. Okay, so we can correct for extinction and get the magnification, and when we do that, we can recover the mean mass profile around galaxies for the sample that we have used. So this is what we find. So now this is coming only from magnification measurements. And it's very interesting because the error bars are getting smaller, and we can compare these results with galaxy lensing and other techniques. And it seems to work pretty well. It seems that we are finding a different slope on small scales and large scales. This is something we need to look at more quantitatively. I just wanted to briefly mention that when people look at this with numerical simulation, this is delta sigma, the mass over density that people constrain with galaxy lensing, predicted from the Millennium simulation. People look at halo mass cross correlation, and again, there is a change of slope expecting at a scale of about 1 megaparsec, which is also what we see in our data. So it will be interesting to investigate that in more details in the future. All right. So now, some extra other implications. I can actually put in the same plot. So here, I'm showing the total mass profile that we got from the magnification. And now for a given model of dust, we know what is the conversion between reddening and dust mass. And because we have shown that the dust that we are seeing seems to be the very standard type of dust, so I can convert the reddening that I measure into an amount of dust mass. And for this, so with our measurements, we cannot differentiate between SMC type of dust or Milky Way type of dust. So I'm showing the two here. But if we use one of these two values, this is the profile that we get for the mass of dust in around these galaxies, average over the whole sample. So it's really nice that with this one technique, we can measure two quantities that are offset by like 4.5 orders of magnitude. And it also shows that there seems to be quite a lot of dust on large scales around galaxies, which was not necessarily expected before. We can compute a few key quantities. If we estimate what is the typical galaxy which gives rise to this dust rending that we see, just assuming that dust is proportional to metallicity and luminosity, then we find that the effective galaxy which gives rise to this rending signal is like half L star. So now if we simply integrate this profile all the way to the virial radius of galaxies with such a luminosity, this is the amount of dust mass that we find in the halo of these galaxies. Again, this is a new number that was not estimated before. We can even estimate the cosmic density of dust by just looking at the number counts of these galaxies and how much mass they have. So this is the kind of number that we get. We can look at the dust to light ratio. People, especially in the lensing community, like to look at the dust to the mass to light ratio. So what is shown here is a reddening to light ratio. So we take this reddening measurement, so reddening of quasars correlated with galaxy density, and we just normalize it with the galaxy autocorrelation. So this actually needs to be compressed into one number because we don't need the wavelength dependence to compute this dust to light ratio, but that's something we can do. And as we see on large case, we find the dust to light ratio which is consistent with being constant. So we reach a kind of cosmological value for this dust to light ratio. And the quantity which is interesting for many people is the opacity of the universe. So we know how much mass we have around these galaxies, how much extinction as a function of radius. So we can just integrate this along the line of sight and see what we get. So first, yes, just a quick remark. We don't care about magnification effects because on average, we know that magnification is unity on the sky. But it's very different for dust because it goes only in one direction. So it's quite important to estimate how much extinction we expect. So this is what we get. So the three different colors are for three different wavelengths. If you look at the U band or the V band in black, for example, just by extrapolating these results along the line of sight, we find that at redshift 1 we have an extinction on average of about 5%. And this is something that is of interest for people who want to study dark energy using supernovae. So in addition, the dust in galaxies at redshift 1 is not expected to be the same, or the amount of dust is expected to be lower. So if we take into account some plausible evolution of the amount of dust in galaxies, and we can map that using magnesium-2 systems, and looking at their dust content as a function of redshift, we can, if we add some plausible model for the evolution of dust, we can have again an estimation of how much dust we have along the line of sight, including intrinsic redshift evolution.
There's a large scatter. I mean,
This is the average quantity.
It's average, right? And,
Yes.
and the scatter is huge.
There is a huge scatter. Yes, we'll have to look at it next. But it means that if you take any sample of supernovae at redshift 1, they will, on average, be extincted by 5% in the V band.
And how much difference does that make to W?
A lot.
But the intrinsic
So-
dust, I mean, obviously, is also very large, right? The host
There's
galaxy
also dust at the host.
Yeah,
There are the
much
two
larger
effects.
than this, right? So
Yes, but I think so. So people correct for dust reddening using
Piece by
with
piece.
supernovae.
right.
The problem is that the RV value, the slope of the extinction curve that they infer, they find an RV value of 1, which is quite extreme. It has never been seen in most of the galaxies that we know. And they don't, so first they correct for the dust in our galaxy because we have mapped this pretty well. But then for the dust correction of the rest, basically, they assume that all the dust is at the host. And they have to do a fitting value where the slope of the extinction curve is a free parameter. And the free parameter that they get is an RV of 1, which is something that people, we have not seen that in galaxies. And people who try to model dust, they cannot reproduce such a value apparently.
That's also not what they got for a local supernova.
And it's not what, RV of 1 has not been seen, but that's what come out of this fitting of supernovae experiment. But the thing is that we know from this that what they could do is also subtract this mean contribution, okay, for which we know the amplitude and the RV value. They have been constrained. At least that's one step closer.
In the presence of large scatter
Yeah.
plus some sort of Malmquist bias, that could be rather risky.
I'm not saying that it's going simple, but yes.
But this average 5% is mostly on lines of sight that go within 10 kiloparsecs or something of galaxy centers, right? This-
Yeah, the mean impact parameter is going to be somewhere around 50 kpc, I guess, but yeah.
Because most of your signal at these larger distances is like a 2 halo term, right?
At 50 kpc, no, it's
No,
clearly a 1.
but out at the larger radio, you said you saw dust out to megaparsecs.
Yes.
But that's
That's in the two halo regime. That's different. Yeah.
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 Also, this interval depends on stochasticity and bias of the dusty galaxies compared to the reference sample. So just like measuring the omega in dust has the same issues as measuring omega in matter by integrating up the mu you get for every galaxy. It depends, because all you're measuring is the variability of the mass correlated to the galaxies, and the unknown is R over B, the stochasticity over the bias. So you measure omega R over B. That's the point you measure with both the mass of omega galaxies and the mass in dust in this case, where the R would be the R of optical to dusty galaxies and the B would be the relative bias. So that could vary by a factor of 2 easily, depending on what you think the clustering properties are, because we know ILS galaxies are biased relative to B-selected ones.
Yeah. Yeah. There is some stochasticity. This is only the observed reddening. So there is a difference between the intrinsic reddening that we would have along the line of sight. That's what you mean?
No, I mean that to convert your number into an omega,
Yeah.
you're assuming that, another way of putting it,
I'm assuming lots of things for this omega dust. I know about that. I just wanted to show the order of magnitude that is inferred from this presence of dust in galactic halos. I'm not saying that it's an accurate estimate for omega dust. There are lots of things that go into that, yes. But the thing is that with the quasars, we are measuring the mean reddening along lines of sight due to galaxies at redshift 0.3. And so we can use that to predict the mean extinction.
again, modulo R over B. So imagine that there was dust out there that didn't correlate with your...
Yeah, yes, and okay, so what we have here is only a lower limit. If we have dust that does not correlate with galaxies, we cannot measure it with our technique.
But also an upper limit, depending if these guys happen to be strongly biased. So if the dust preferentially lived, it's strongly biased relative to the reference galaxy. It can go both ways. It's R over B. R can be less than 1, B can be greater or less than 1. So it can go both ways depending on what you think the cross correlation is between dust and galaxies.
Right, so that, for that sort of thing, you'd really want to break your galaxy sample down and look at subsamples of the galaxies and throw those in to try and tease that sort of effect out, right?
Yes.
So that's,
Yeah, that's the next step, yeah.
yeah.
Just looking at different types of galaxies, looking at clusters or not clusters, etc. Yes. This is just the first global average that we got of the data.
But sorry, just really, are there simulations of situations where you've seen R's that are more than 100%?
Okay, on scale then, you know, at half megaparsecs, where this is being measured, R between blues and reds are 0.7 or something, other than that. I mean, or between IRAS and between optically selected. You know, I don't know whether all the dust preferentially lives in IRAS-like starbursts, for example, at the extreme, in which case that has a bias of order unity, you know, order 2 or something, relative to red galaxies, for example, right? So, you know, the factor of 2 we can certainly squeeze into here, even with known effects between dusty and non-dusty objects.
Okay, but I mean, yeah, splitting the sample in different galaxy categories, I mean, we'll be able to investigate this in more detail in the future. But at least, I mean, those are the first constraints on how much dust we have on large scale around galaxies. I think that's already quite interesting. Oh yes, so we talked about that. This is just, yeah, showing a Hubble diagram. So this effect is basically going to be included in those data points, and this is at the 5% level. Okay, so just to finish up quickly. So, yeah, I think we have, I hope we have convinced you that we can come up with this new tool to plot the dust distribution in the universe. So this is interesting because it allows us to correct magnification measurements for dust extinction. And the corrections are not negligible. It's like 1/3 or 1/5 depending on the wavelengths. Then we have this new tool, so which allows us to look at the different types of correlations between dust and light, dust and mass. So we can now probe these distributions in more detail. As Ryan said, the current analysis is only based on, this is still based on DR3. We can now push that to the new data sets available with Sloan. There is already a factor of 5 with the increase of the number of quasars between the sample we were able to use for this analysis and what is available today.
So that's more area and plus higher density.
Yeah, so yeah, Gordon, Richards, and others, they have been able to improve their ways of detecting quasars. So we can gain on different directions. And yeah, in the future, so we don't need any spectroscopy to do this kind of measurement. If we have this type of 5-band filter system, we can select quasars, assign redshifts, redo this measurement. So there will be plenty of signal to noise coming out of this. So to summarize, so Ryan showed you that so we can detect magnification. I hope it was convincing because we do see the expected dependence on the slope of the number counts. We can find the expected excess of quasars, the expected deficit of quasars. We can now prove that on an impressive range of scales from 20 kpc to 50 megaparsecs. We may be starting to see these changes of slopes that are expected by lambda CDM halo mass cross correlations. And more importantly, on top of the magnification, we now see the effects of dust extinction. So we have this first detection of dust on large scales around galaxies. We can see that the wavelength dependence is what we expect for standard type of dust. This implies modulo a factor of 2 maybe. We have to look at this in more details. But basically, we have some knowledge of what the mean opacity of the universe may be. So it's something that people might want to include in their dark energy constraints from supernova. And yeah, just to finish, I think that these quasar-galaxy correlations, they are providing us with this new tool to probe not only the magnification, but the dust distribution in the universe. I'm going to stop here. Thank you.
Tommaso?
I have two questions. One is, at what scale do you think this measurement breaks down because of crowding or photometric biasing by the foreground galaxies to extend the life of all the quasars? This is question number one. Question number two, your quasars are color selected, and then you want to measure color correlations. I guess at this level it's probably negligible selection bias, but at what point do you worry about that?
Okay, so to answer the second question first, yeah, so the magnitude changes that are due to dust or magnification, they are really small. And especially for the colors. So the sample is magnitude selected and color selected. So we have done some tests with Gordon Richards. We took the quasars, we added some extinction with different amounts of extinctions, and then we used Gordon's pipeline to reselect the quasars and see whether the measured reddening corresponds to the observed reddening. And in this regime, it's fine. If you go to much larger values of extinction or reddening, then you start to see a difference between the observed reddening and the reddening that you use, because quasars start to be missed because they become too red. But we are not in a regime where quasars are missed because they are too red. We are in a regime where they are missed because they become too faint. It's basically crossing the limiting magnitude that changes things here. So on small scales, so maybe this is a question for Robert. So if we push the measurement down to even smaller scales, then we start to see some very funny things. When this is probably due to deblending issues and so on. I don't know exactly at what scale the measurement breaks down. Yeah, this is the effective.
We're still above the deblending effects. If you properly mask out the really bright objects, the deblending effects kick in at about. It depends a little bit on your sample, but somewhere in the regime of about 3,000th of a degree. I mean, I make you convert that into your head. Yeah, no, I understand, but that's what I'm saying is you're throwing things out of your sample because the blending has broken down, and Robert is really good, but he's not perfect. Okay, Robert's perfect. It's our fault that we lose those objects. Yeah. So we're still. I mean, we're still angular scale wise. We're only going down to about a factor or two bigger than that. So crowding is not an issue at this point. I mean, if we tried to push it deeper in angular or smaller angular scale, yes, we would run into that, but we're still healthily above that limit where it should be a real problem.
I mean, these are really scary small effects that are being measured. I'm sorry.
I mean, it also it's worth saying that we are very much helped by the fact that our sources are point sources.
Point sources, yeah.
And those are much easier to disentangle.
Yeah, you can define the magnitude of point sources much better than extended objects.
Right.
So.
But these are scarily small effects. I mean, you're looking at 1 millimag sort of levels, and you haven't talked about all the agony that you've gone through trying to understand the impact of small leaks through in the star-galaxy separation failing at 21.3 and all that sort of stuff. So, as far as I know, it all hangs together, but
Yeah.
I certainly wouldn't believe this as
Yeah.
presented. as
Sure,
opposed
but
to-
one way of investigating these systematic effects, so you can look at this effect for bright quasars and faint galaxies, for example, where you know that relatively the effect is those contaminations are going to be much lower. So that's, yeah, we have done these things.
Correct?
Yes.
So if you measure distance letter in different places on the sky, would you expect your outcome to depend on your large scale structure?
Yeah, I mean that's yeah, there will be some extra variance due to dust following large scale structures, but on large scales the effect becomes really, really small. So
Ready?
So presumably you know the PDF of just extinctions to quasars independent of your sample. You actually know the mean extinction to the quasar sample without doing any of this cross correlation. So the one thing you would learn by cross correlating is the redshift distribution of this extinction under the assumption that R and B don't evolve with redshift, which who knows, but let's say you make that assumption. So the question would be, since you actually have one of these for the galaxies, what does that look like? Well, what is the distribution of the dust as a function of redshift from here? Maybe you don't get all the way to all the quasars, but you surely do to some of them. And does it add up? Does the dust along planet lines, if you just do this cross check, when you add it up, does it give you the same extinction as just the mean volume weighted from the galaxies, quasars?
We don't have photoses for these galaxies, or we do, but we didn't use them at all. All the galaxies are in one bin, so we haven't looked at slicing it up that way.
And what about the mean sum? Just sum up it takes the mean extinction of all the quasars that tells you what AB is independent of the cross correlation. That number, before you cross correlate, what's the number?
how do you get the mean extinction of quasars?
One just takes if you got the extinction for every quasar, just takes the average, isn't it?
How do you get the extinction for every quasar?
Well, that was put in. You measure a reddening for every.
No, because it's noise dominated if you take
Yeah.
one quasar.
We only get a number when we do this with 100,000
Ye-
quasars.
Yeah, it's only the average over many quasars that can be measured. I mean, quasars have a huge scatter in colors and luminosities. So it's only after doing this correlation with 100,000 quasars that we can find excesses that correlate with galaxy positions.
More precisely, you only measure the relative.
I measure only the relative. This is only the reddening. This is the dust that correlates with galaxies. If there is a plane of dust, we are not sensitive to it at all.
So do you know a way to measure extinction of quasars individually? Because I'd like to know. I'm not. I just don't. I mean, can you? Does anybody know?
Well, there was a paper, when the supernova results first came out, it was like, could it just be dust? And there was at least one paper where a deep X-ray observation was taken on some relatively high redshift quasar, and they looked for the scattered X-ray halo that would have been produced by that dust. And found something that I think ruled out the possibility that all the dark energy was actually just dust.
Yeah.
That's the only method I
So we need lots of deep X-ray.
It also turns out you need to know PSF from the X-ray telescope. It's much better than it's normally known.
You can do something with less distance precision with multiple image quasars, perhaps.
Because that's also differential.
That's differential again.
Right. So changing the topic a bit, the dust masses, I'm trying to figure them out in my head. Does it lead, I guess my question is, does this lead to any surprises about the evolution of the stellar populations in the galaxies in terms of the amount of dust they must have produced and the enrichment of the IgM?
We haven't looked at that in much detail. I know that those numbers are not crazy. They are I mean, the amount of dust, people can measure the amount of dust that there is in outflows in M82, for example. And if a galaxy goes through this kind of burst of star formation 10 times in its life, then you can eject as much dust as what we see. So
you didn't show that the dust is living intergalactic. It could be living in satellites, as you say, right?
yeah, so we don't know about the origin, yes.
Right.
But that's just a possibility. I mean, what I'm saying...
It could be just the satellites, which seems fine as well, because your dust to total mass ratio is 10 minus 4. So if you just take omega and stars and 10 minus 2 and it provides 1% metallicity, that's what you get, right?
Yeah, so that's just, different possible of origin.
That's just the dust of galaxies you know exist. If you add those, doesn't that account for all the dust pretty much, even without intergalactic?
I think if you add the dust just from satellites, you are not reaching this value.
All called it 1 megaparsec. It's the galaxy like N31 that is the dust that you add to our galaxy, right? So that's what you measure it like. Things like N31 when you look at us, that all goes into the statistic.
Yeah.
Yeah, right. I mean, the only difference is that the picture of the cigar galaxy from the Spitzer is really cool, and then we get to talk about dust outflows. If somebody has a really cool picture of like satellite galaxies.
One last question for Brice and Ryan. All right, so let's thank them again.